All right. Thanks, Randy, and thanks again for allowing us to come on here this morning and talk some more about severe weather, which doesn't seem much like a day that we should be talking about supercells, but we'll do it anyway because I guess it'll be here before you know it. So, yeah, we're going to take a look, another look at the storm relative velocity enhancement airstream, but a little bit different take on it, like how it's oriented to the radar and that sort of thing, and sometimes it can look a little different. So just getting right into it here, what is a SRVE? It's an asymmetric signature. It originates from the forward flank downdraft region. You can kind of see here in the white oval, both on the storm relative velocity image there and also the reflectivity. In this particular case, the radar is located to the north. This is from the Paducah radar from 2016. And so this asymmetric signature in this particular case shows up as an outbound signature. But it's an enhancement best seen within probably 40 nautical miles from the radar. Like many other features that you should be concerned with when looking for tornado genesis. And that's really where we're going with why this is important. But the important thing that we'll talk about today is it may not be seen in this fashion if it's not located in the best shape with relationship to the radar. So, but we're going to throw you a little bit of a plot twist right away, and that's that we've changed the naming convention a little bit. We now will refer to it as the left flank velocity enhancement. So just a little plot twist there for you. So again, just kind of outlining the region here that we're talking about. The black outline gives you the 40 dBz reflectivity line. And so kind of looking at this, in this particular case, this is a different radar image. This is an inbound signature now with the radar located to the south-southeast of this particular storm. So, and the other thing that we'll cover towards the end here is you'll notice here for the LFVE that I did not outline the entire inbound or the green signature here, and there's a reason for that, and we'll touch on that just a little bit at the end. So again, the left flank velocity enhancement is an airstream that aligns pretty closely with what researchers such as Beck and Weiss have shown with the left flank convergent boundary, hence the name change. We feel that it's better to be consistent in the naming convention, and this kind of lines up best with that peer-reviewed research and others as well. So again, but we're looking at the same area here. In this particular instance, it's an inbound signature originating from the forward flank downdraft region. The problem with the LFCB is that it's, pretty difficult for the radar to determine where that is a lot of the time, depending upon where you are in relationship to the radar. So instead, you more likely will see the resultant airstream that's associated with the LFCB based on the resolution of the 88D. You're not going to probably see, depending upon, again, how close you are and your radar viewing angle, you may not see this convergent boundary in the left flank region. So we're looking for that resultant area here as it flows around the backside of the low level and under the low level mesocyclone. So further looking at the Beck and Weiss research, they found here that the resultant horizontal velocity does indeed flow along that and on the cool side of that left flank convergent boundary, again, towards and kind of through the hook echo, converging under the low level mesocyclone. And this is again in cases of supercells that produce tornadoes. So throwing in some more research here, again, this whole idea of a descending airstream that originates from the forward flank, it goes back a ways, and this is been touched upon with the Markowski and Richardson paper from 2014, looking at the trajectory coming in and under the low-level mesocyclone where the best dynamic lifting occurs. And then the little insert there from Parker and Dahl 2015 that looks at how this trajectory descends as it moves through the or towards the hook echo there region, and then turning and converging under the low-level mesocyclone. So again, just trying to orient where we should be looking for this particular airstream. Again, this is going back to the Beck and Weiss research. They modeled several low-level boundaries here. They noted that the rear flank gust front formed first in supercells, which you can see as a solid gray line here in the image. And then that was followed by the left flank convergent boundary, and then the forward flank convergent boundary. And so the forward flank convergent boundary becomes important because most research looking at the SVC, or the streamwise vorticity current, suggests that it forms along and on the cool side of the forward flank convergent boundary. Again, here noting Schuth et al. From last year, the research done by them, indicating that as well. And the important thing about the SVC is that it contributes to the mid-level vertical vorticity. So it actually is an ascending airstream that contributes to the low-level mesocyclone. But however, Merdzek et al. And others have noted that the parcels destined for the tornado-like vortex that they model in their high-resolution simulations, those parcels are collect along boundaries that are co-located with prominent horizontal buoyancy gradients, much like you would see in the forward flank region, where rivers of vertical vorticity are formed, again feeding that and descending into the low-level, under the low-level mesocyclone. And there's that LFCB there. And then here's just a little bit more research from Coffer and Parker, suggesting that they actually were able to find some of these rivers of vertical vorticity, although some of the field projects haven't necessarily found these as well as what's in high resolution simulations. But nonetheless, this area seems to be very important as it flows into and on the backside of the low-level mesocyclone. So again, going clear back even to looking at Lee Orff's high-resolution simulations of the 2011 El Reno EF5. Again, noting the SVC and that it's an ascending airstream that works into the low-level mesocyclone. But noting that the parcels that make it into that tornado, even in their simulations, actually occur or originate from deeper within the colder air of the forward flank region. The SVC, however, operationally, we've kind of noted that it aligns very similarly to where you would see the ZDR arc, again, along and just on the cool side of the forward flank convergent boundary. So this particular image is kind of a screenshot, but it's adapted from Finley 2018 through personal communication there. Again, just further outlining the research that really looks at how all this comes together. Really, this area from the forward flank in the rain-cooled air is adjacent to the horizontal buoyancy gradients that exist because of that precipitation downdraft that exists in the forward flank region. And, kind of by definition, this is an area of baroclinic vorticity generation. This particular image is adapted from Rotuno et al. From 2017. Again, just kind of reiterating some of the same thing. Some of this is kind of repetitive for a reason, and that's because there's really quite a bit of high resolution modeling that has taken place, all kind of suggesting the same thing, where the parcels that make it into the low-level mesocyclone actually kind of originate in that SVC along the forward flank convergent boundary, while those that make it into the tornado-like vortex, which is what they call it in simulations, actually originates from deeper within the colder air. And so there again, another look at kind of a cross section in the the Parker and Dahl image there, the 3D image showing the descending airstream. Now, just kind of putting it all together, again, those parcels acquire baroclinically generated vorticity as they move rearward in the supercell. They originate from the forward flank region, and as they turn southward, the parcels briefly ascend before more rapidly descending within the outflow. And the important thing to note there is that baroclinic vorticity in some research is actually suggested to be crosswise, which allows the vorticity vector to be kind of tilted more on the back end and tipped it off the trajectory, which allows it to be tilted and stretched by the low-level mesocyclone. So putting all this together, this is kind of what Aaron and I have come up with for a conceptual model, trying to outline kind of where some of these different airstreams exist and where they kind of originate from. And of course, the one we're focusing on is the one there in yellow, the left flank velocity enhancement. Also important to note the convergent signature under the low-level mesocyclone here, because that can show up, again, depending upon how close you are to the radar and the radar viewing angle. This becomes important to note those cases that we've looked at that are more likely to produce a tornado than those that aren't. And this really goes back to the buoyancy within that same LFVE region. If the buoyancy is not favorable, oftentimes you'll see that convergent boundary kind of blowing right through that updraft region. So again, this is the region we're looking for, the kind of resultant flow along the LFCB there. But again, depending upon where you are in relationship to the radar, it may or may not be able to see even the resultant airstream. For example, in this case, where the radar would be located to the east, it would be orthogonal to the radar beam and likely not show up very well at all. Again, this is kind of going back to the conceptual model. This is why it's really important to understand a conceptual model, especially one that incorporates all these different airstreams, to really know what's going to make up that velocity signal and where it originates from. Because at any given time, and we'll look at this more towards the end, a particular velocity snapshot from the 88D could really contain airstreams that originate from many different locations. So here's an example where that is the case, and we'll look at the progression of this particular tornado, an EF3 that was from the 25 March outbreak of last year down in Alabama. This particular one had a path length of about 50 miles on the ground for quite a bit of time there. And from the Birmingham office, here's a look at their path track there and some of the damage done. So we're going to start back at 1746 UTC. And just to get you oriented here in this particular floor pan, all I have in the upper left, reflectivity at ½ degree. Upper right is storm relative velocity at ½ degree. And the bottom right is storm relative velocity of 1.8 degrees, and the bottom left is ZDR. So again, supercell characteristics, obviously with this particular storm. This storm had produced tornadoes for quite a period of time earlier, and then again later. At this particular time, at least according to the damage surveys, there wasn't a tornado on the ground at this time. We're located fairly closely to the radar, but you can see that the storm is located from KBMX here. It's located almost straight west of the radar. So what we're really looking at here is we can kind of identify this low-level mesocyclone on the 1.8 degree storm relative velocity image here, which I've superimposed on the lower level storm relative velocity. And then this region here that shows up that I have outlined with the white line here kind of shows up as a minimum, but you can see certainly a really good outbound signature here in the pinks and even orange color immediately adjacent to that. But just kind of downstream from that is a velocity minimum. Kind of exists right in that area that we were been talking about, where that left flank convergent boundary would be and the resultant airstream would flow according to the conceptual model. So here again is kind of a look at the Beck and Weiss high resolution modeling research and kind of identifying those same regions within the supercell. So looking at the half-degree storm relative velocity even a little bit closer here, you'll note that this outbound signature seems to be aligned along and pretty close to that forward flank convergent boundary, and certainly behind where the forward flank reflectivity gradient is, or kind of adjacent to it, I guess I should say. So based on the conceptual model, we would think that this outbound signature is probably dominated by the SVC. So it's important to understand that, because that's an ascending airstream and not a descending airstream like what we're looking for. So the descending airstream instead, the LFVE, would be oriented from, again, deeper within the forward flank region of that supercell, but unfortunately orthogonal to the radar beam. So hence you're not going to see a whole lot of return from that particular region within velocity signature, but instead is kind of overwhelmed by the SVC. Again, this is where understanding the conceptual model is important, because we're looking at that orientation of the LFVE being perpendicular to the radar beam. So again, as I mentioned, little of the velocity returned to the radar is from the LFVE if in fact this airstream is kind of oriented the way the research suggests it should be. In addition, that LFVE is descending, which of course you also can't tell from the 88D by itself. And since we're looking at the lowest scan available, you're not going to see that. Instead, we have to remember that this is all the information we get from the 88D is a snapshot in time. So you really have to kind of understand that conceptual model and note that the SVC is an ascending airstream, whereas the LFVE should be a descending airstream. So we'll jump ahead to 1824 now. Tornado is ongoing, and again the 4 panel is the same, with in the upper left reflectivity, upper right is half-degree storm relative velocity. In the bottom right this time though is, since we're a little closer to the radar, I've gone up to 3.1 degrees on the storm relative velocity, and then still half-degree ZDR in the bottom left. But you'll note the orientation to the radar, which is a little bit off the image here in each of these cases. You can kind of see it show up better in the velocity. But the radar is located more southeast of where the supercell is now. So again, we've kind of outlined here where the low to mid-level rotation would be, the mesocyclone. And then we kind of orient ourselves again to the left flank convergence boundary and where that should show up in relationship to the conceptual model of the supercell in tornadic situations. Now you see, though, that we can see a broader area of inbound velocity headed toward the radar. So that again depends on the orientation of the radar. So if we look at again this area that the high resolution modeling suggests should be inflow into that hook echo region around the backside of the low-level mesocyclone. So that's kind of the area we're looking at here. That's kind of flashing in that that white color there. So looking a little closer again, tornadoes ongoing at this point. So that's kind of an easy thing to detect at this point. But it's important to note that the radar beam is oriented more favorably to be able to detect the left flank velocity enhancement, coming almost parallel there, or anti-parallel to the radar beam, shows up a lot better. However, so this is again that area in the research that you would see flowing around the backside of the low-level mesocyclone. However, what you don't see is the SVC, and the reason that would be is because, again, based on the conceptual model, we know that the SVC should be aligned along and on the cool side of the forward flank boundary. So this is going to be more orthogonal to the radar beam instead. So you're not seeing that really highly dominated signal by the SVC that we saw earlier when the storm was located to the west of the radar. So again, this is just radar orientation, and knowing the conceptual model is important to understand what you should be seeing and where it should be originating from. So getting kind of repetitive here, showing you the Beck and Weiss high resolution modeling there, but it's important to understand that, you know, these are the things we're not seeing with the 88D. So it's up to us as the radar operator to really be able to make this connection and know how it's useful. So again, just kind of the two snapshots, 7 minutes before tornado genesis. If you're looking for the LFVE to be a nice, well-determined inbound or outbound signature, with this orientation, you're not going to see it because of the orientation to the radar beam. But instead, knowing that conceptual model is important because you, again, knowing where the radar is located, you would know that indeed it most likely would show up as a minimum in the velocity instead of something more enhanced. Here's another case from Dodge City back in May of 2019. This is just right before tornado touchdown here, but another case where in this case the radar's located to the east or to the west. The radar is located to the west-northwest of the supercell. So again, the LFVE would be oriented orthogonal to the radar beam, and so it doesn't show up very well until it starts to make its turn underneath the low-level mesocyclone. So again, knowing the conceptual model is important here because it'll help you understand why there are some outbounds here like we would expect it to be, but the reason is because that's where it's making its turn underneath the low-level mesocyclone. Yet that airstream originates from much deeper within the forward flank region. So we'll just step through fairly quickly here that that Shelby Bibb County case that we looked at earlier. So this is back at 1736. Moving ahead to 1746 now, 10-minute jump here. The beam height center line is at about 1670. So kind of outlining this minimum area here again with the storm located to the west of the radar. Again, we're that outbound signature that you see so prominent here is actually dominated by the SVC most likely. So now we've jumped ahead another 10 minutes, tornado obviously on the ground here. So looking for anything at this point prior to tornado genesis, we're obviously, you know, the train's left the station on that. However, you can see how the orientation or the velocity returns here are starting to show a little bit of inbound signature here. And that again is as this LFVE is making its turn under the low-level mesocyclone. And also note where the convergence would be here, kind of on a literal sense where the inbounds meets those strong outbound signatures. Really strong convergence happening here underneath the low-level mesocyclone. That gives you, a clue, even though we know tornadoes ongoing here, that reoriented vorticity into the vertical is really being stretched and tilted pretty strongly right now. Again, as the radar starts to get a little closer to the radar, we're seeing a little bit more beam height centerline now under 1,000 feet. And you can see the turning under the low-level mesocyclone even a little bit better now. And you can also see kind of the zero isotop or light green colors here showing up here. We'll talk a little bit more about those. And then as we get a little closer, I'm starting to see more of that inbound signature. And then I've kind of jumped to a different orientation here just to help kind of visualize this a little bit better. The inbound signature, now that the storm's off to the north-northwest, certainly dominated much better by the LFVE, but you notice by the black line, that hasn't changed where it is in relationship to the supercell location here. It's been in the same place the whole time. So some take-home points here as we're getting further along. I'm just going to kind of go through those quickly. Here is our conceptual model that Aaron and I have put together for the CWIP. You'll see this, by the way, in the radar feature catalog entries that we'll have coming up over the next couple of months, and also in the guide that we sent out earlier this year for the tornado warning guidance that we have there. But again, all the research to back up kind of this, where these locations are of the boundaries, as well as the airstreams associated with them. So, looking at all the points that we discussed here, again, the asymmetric airstream, and that's important too, because we're not looking at a nice well-defined VROT signature here in the beginning stages prior to tornado genesis. It's really an asymmetric airstream. It's oriented from the forward flank, and it's moves towards the developing hook echo and under the low-level mesocyclone. Again, can be seen as an inbound or an outbound signature, depending upon where you are in relationship to the radar, but also cannot be seen hardly at all if it's oriented orthogonal to the radar beam. And like most other things, including the ZDR arc, it's best located close to the radar. If you can get under 1 kilometer, that's even better. So again, you can't always visualize these details with the 88D. We're just given snapshots, and that's why it's so important to understand the conceptual model and what it means to tornado genesis. Here's all the gory details of the research associated with all those statements that I made on the previous one, and I can make this presentation available certainly so you can have at least a start at if you want to research this information. So just quickly touching on what I had commented on before, here is just a snapshot from, again, that Mayfield, Kentucky 2016 tornado case. Again, not the most recent Mayfield one, but going back to 2016, a particular storm relative velocity scan from the 88D can really contain several airstreams. If you think of this kind of on a plane of what the radar is seeing, that's what makes it very difficult and critical in understanding the conceptual model. This velocity signature could be made up of the LFVE, could also be the the stream-rise vorticity current, but it could also be associated with the rear flank internal surges, which there's other research on, going back to some of the other work done at NSSL and SIMS. But here in the bottom image here is an image I took from Patrick Skinner and Dixon from their SLS presentation, showing again these boundaries and how they can look different depending upon where you are in relationship to the radar. And so what they're doing some exciting work by trying to fabricate a velocity image much like you would see with the 88D. And Aaron and I have kind of tagged up with them. And so we have some ideas going forward about how we can maybe pick their brains and kind of collaborate on research as to what we're seeing and what that all means, further down the line as far as simulations go. So again, just kind of pointing out how all these different airstreams can exist on a particular plane that you might see a velocity slice from. You can imagine here from Lee Orff's fantastic work there. He's got all the parcels outlined here and all the different ways they're going. So it's kind of impossible to tell unless you understand that conceptual model. So I want to give Aaron some time here. So we can certainly take any questions after he's done, now that I've rambled on a little bit too long.